try. This time I was successful. So, Carlo, please.
Okay, so please, in case there is any issue with the microphone, please let me know, because sometimes there is a problem with this.
Okay, thank you. Yeah.
All right, thanks. So I will start from actually not start from where I left yesterday, but I will develop in more detail something that I quickly said yesterday, mainly because I realized that I may be wrong, but it is not very common to know much about convex functions and the topics that I used yesterday. So maybe it is better to spend a little bit more time on it. I went too fast yesterday because I thought that yesterday was my last real class, and that today I had to switch to examples, exercises, or something. But I was told that this was only the plan for the preliminary, for the old version, so the planned version, the online, the live version in Swansea, not the online one. So I will then repeat, actually treat from scratch something that I just gave for granted yesterday. And we start with some notions of related to convexity that I definitely went too quickly about yesterday. And so let us first see geometrically what is the interpretation of the meaning of convexity, which is actually not difficult at all. But so let us suppose we have just a convex function. We said that, let us repeat our definition. The definition was that f of lambda x plus 1 minus lambda y is less or equal than lambda f of x plus 1 minus lambda f of y. And this should be true for all x and y in the domain C, for all lambda in 0, 1. So, of course, this definition that I gave yesterday was valid for any convex set in a general vector space, but since we are mostly interested in the derivation of simple analytic inequalities related to convexity, we look just at the case of functions of one real variable for the time being, although a suitable generalization of the arguments that I'm giving today applies also in a much more general setting. So the interpretation of this is simply that if I take this point x and this point y, and I look at the segment joining the point x f of x and y f of y, then the whole segment, which is parameterized by lambda and given by this expression, lies above the graph of the function f. Okay, so this will be the graph of the function f for lambda running between 0 and 1. This will be the graph of the segment joining the point x f of x, y f of y. So we have this very simple interpretation, and now we look at what happens if we compare some quantities of interest given another extra point here that for the time being we don't need to give a name to, and we look at another two segments, and in order not to be distracted by useless things, we just remove the graph of the function f itself, and we look only at even simpler situation. We look at the situation where we have 3 points, let's say 1 point here, 1 point here, 1 point here, and we give names to this point. This is A, this is C, this is B, and we look at the affine functions that join these points. And simply by elementary Euclidean geometry, we see several things of interest, but one that is enough for us is the following, that we have an equivalence between the following facts. So let's say the following facts are equivalent. 1, B is below the the straight line AC. So of course below is not a mathematical expression, but if you formulate the concept in terms of the usual translation into Cartesian geometry, everything is fine. So you simply have to say that you give the coordinates of this point, then you write the equation for the line, the straight line, the affine function passes through A and C, and then you write a suitable inequality between the value of this coordinate and the value of this coordinate. So there is no point for me to do this, but it is just to mention that everything can be made precise. And also everything can be made precise in the following expression, that the slope of AB is less or equal than the slope of AC, and 3, that the slope of AC is less or equal than the slope of BC. Okay, so now it is a rather easy exercise to check the following fact, that if we put together the definition of convex function and this simple observation that come just from the usual algebra of triangles, geometry, plane geometry of triangles, we land to the following proposition. So, which is just a consequence of this observation and the definition of convex function. So we have that f, let's say C to R, where C is interval of the real line, of course. Then we have the following things, that the function is convex, so f convex, if and only if for every a in A, the function x, f of x minus f of a over x minus a is increasing. Okay, so you see simply that the interpretation will be so if we relabel the points here, we could say that this could be, let's say, A. I replace this with A. This I call it x1, and this I call it x2. And so this thing is just a translation of these two relations between slopes. Okay, so again, this is really up to now, this is just essentially a reduction of this convexity idea to let's say high school geometry. Okay, so in spite of being fully elementary, this has very interesting consequences, and the first one is the following. So we have a simple corollary which says that if you take f c to r with the same notation as before, with again the function f being convex, and you take a point I which is in the interior of C, sorry, I use the letter C, in the interior of C, or if you like, you can just assume that C is open, then you can remove this condition. Everything will be the same. Then we have the following implication, that so there exists the derivative of the function f at the point A from the left. There exists also the derivative from the right. And as you all know, or also are supposed to know, the existence of these two derivatives imply that f is continuous at A. And moreover, we have a relation between them, that the left derivative is dominated by the right derivative. Okay, so the proof of this is very simple, but let us give it. So as I said, this implication doesn't need a proof. This is something that we know. So let A be an element of the interior of C, and take x larger than A. then what does this imply? This imply, as we know, that the function x, well, it's not an implication, it's something that we know. We know that f of x minus f of a over x minus a is increasing. So we are going to use these facts. Is increasing, and moreover, this function is also bounded from below on a neighborhood. So I'm not going to write it. I'm just saying this is bounded from below on a neighborhood of a because it is enough to take any y less than a. Use the fact again that this function is monotone, and this expression is bounded, as we said, from below by just f of y minus f of a over y minus a. Then what do we have? Well, we have a monotone function which is bounded from below, so we can take the limit, and therefore this is very easy. By the way, the limit coincides with the infimum of this function for x strictly larger than a, and so this implies, so this simple observation together imply that indeed there exists the derivative from the right of the function f at the point a. If you reverse this argument, you reverse. But I mean that if you look at the situation where x is larger than a, so let's say first point and then second point of the proof, you look at the case when x is larger than a. By repeating the argument, essentially the same argument, you will obtain that you get that d minus f a exists as well. Moreover, so now we have the proof of existence, but we need to prove this relation. So what does this relation mean? This is true for all y less than a. So you see that that this immediately, well, is larger or equal, in fact, not necessarily larger. This implies immediately that f of y minus f of a over y minus a, this is dominated by d plus f of a, right? So you fix y arbitrary, then this is true for all x larger than a. Then you take the limit as x goes to a from above, and therefore you end up with this expression. Okay. Moreover, you get, so maybe let us write here again for all y larger than a. By looking at the proof for this argument, you obtain from the same argument, but let's say with reversed signs, you get the other implication. You get the implication that d minus f a is less or equal than f of x minus f of a over x minus a, and this is true for all x larger than a. And now you see immediately how the proof goes, because then you take the supremum on both sides for x larger than a, and this produces just the derivative from the right. So we have that as an implication. By taking the supremum or the limit from x from above, you get that d minus fa is less or equal than d plus fa. Okay, so these very simple inequalities have a particular interest for us, apart of being interesting by themselves. By the way, you see that we proved that without any continuity assumption, we proved that continuous functions, that the convex functions admit right and left derivatives at all points of interior to an interval, which is not quite obvious from the definition, but very easy to check as you saw. It follows also from the relations that we just established that maybe should I? Well, let us call it remark. It is not really. It doesn't really deserve to be called proposition or anything. So we have the following fact that if we take any point b larger than a, both interior to c, then we have that f of b minus f of a is larger. B minus a, sorry, is larger or equal than d plus f at a2. And the reason is quite simple, because this is nothing else than the inf of f of x minus f of a over x minus a for x larger than a. So this is automatically true. It's very easy. Then if you look at what happens for d minus, then you would get also that you get an upper bound, so you would have that f of b minus f of a over b minus a. So we gave an upper bound, we can give a lower bound. This is dfb, d minus fb. Okay, so you get exactly the same argument. So this is you just look at the left, so this is the supremum, so you repeat the same thing. So you everywhere where you have minus, you have plus, where you have inf, you have sup. So everything is quite simple here. So this observation allows to prove, well, let's say a lemma. So let alpha be any element belonging to the interval d minus fa, d plus fa. Where again, remember that a is a point interior to the interval, f is a convex function, so always the same assumption. Then we have the affine function, then the affine function, I should say actually the graph of the affine function, but I just write like this. So the affine function, which is defined by y equal alpha x minus a plus fa. And then here I use an expression that is commonly used in analysis, but by itself makes no sense. Later we explain what it means. So touches from below the graph. I should say the graph of the function f. So, but I just say the function f at a. What does this mean? Well, it simply means something like this: that if you have even a very regular function, a very regular function, convex function like this, then you take any alpha which is between the left derivative and the right derivative at the point A. So suppose that this is the point A. So, and you take any straight line, so any graph of a affine function with an alpha which is between d minus and d plus. So you see that d plus is the derivative with this slope. Of course, here I could have chosen something, let's say, a bit less extreme than this, so something like this, for instance. So, and you see that you take all straight lines going through the point, and all they touch from below. What does it mean they touch from below? That on the point A, they have the same value, and on all other points, so maybe I should have, so this is our function. On all other points, this affine functions lie below the graph of the function f. Okay, so this is the graph of the function f. Again, lie below simply means that whenever you have something like this, then this y should be less or equal than f of x. Okay, so this is just a way to say things quickly, avoiding to write plenty of things, but everything is entirely rigorous. So this fact, of course, is just written let's say, it is written in a language that definitely needs the proof, because this is not really meaningful. So, but the proof is very quick. So I just give one case, the other one I leave it to you. So assume that x is larger than a. Then we have that f of x minus f of a over x minus a, and this is comes from here. This is larger or equal than d plus fa. This obviously implies that f of x minus f of a is larger or equal than d plus fa multiplied by x minus a. But since alpha is less than that, then this is larger or equal than alpha x minus a. And so you see that f of x is larger than the y corresponding to x. Okay, so we have in fact proved this thing that touches from below. Well, touches from below, why? Because you look at the value at a of this function, of this affine function, and it is exactly f of a. Okay, so we have proved the touching from below relation for x larger than a. Then you look at x less than a, and you use the fact that x minus a will be negative, and then you use the other inequality that a is larger than d minus fa. So when multiplied by a negative number, everything turns out to be with the correct sign. Okay, so we have proved this thing. You can also prove that, in fact, this is an if and only if characterization. I would probably leave this to you, but I will write the full detail in the notes. In the full characterization says that an affine function touches the graph of G from below if and only if it is of this form. Okay, so that is what I meant by saying that there is an if and only if characterization. So the important consequence for us of this fact is the following, that we have a very important lemma, maybe I just call it proposition, that I mentioned yesterday in a too quick way. And it is the following. Suppose that we have FCR as before, convex C interval. So I repeat it maybe because it's important. C is an interval, let's say C open interval. Then we have the following. Then F can be written, then F is the supremum of all its minorant affine functions. Minorant simply means that the supremum lie below the function f. So the reason why the previous observation, the previous lemma was important is that we know that the family of minorant affine function is not empty. Okay, because for any point A in the interior, that's why I assume that C is open, we know that left and right derivatives exist. So you take any alpha in the interval d minus f, d plus f at A, and you get a minorant affine function. In particular, it is more than that. It is not just minorant, it is also touching from below. But the important observation is this. So we could write in particular that, actually this proposition doesn't need a proof because the proof is the previous lemma, okay? So proof, previous lemma. So the important fact is then that we can write that f of x is equal to supremum of, let's say, aix plus bi, where I is a collection of numbers. So there is an important observation here that I would like to make, that is particularly important in certain settings. I don't know whether we will be able to talk about them today, but it is interesting in its own right, that in general, we cannot claim at all that this set of indices here is countable. However, you see that this, of course, can be simply written as supremum of aix plus bi over the families ai, bi, right? And these families simply are a subset of R2. And now, by an argument that we have already used a couple of times during the previous lectures, well, we know that there is a very nice countable subset of R2, which is dense in R2, which is nothing else than Q2. Okay, so therefore, since this is a continuous function on this set, we can replace R2 by Q2. Okay, so the fact that we can take a supremum of a number of families that is countable is very useful. Although for the very basic proof of the general Jensen's inequality that I showed yesterday very quickly towards the end, this observation is not strictly needed, although I will try to mention where it is needed. So a very important application of this is the Jensen's inequality for integrals, which goes as follows. So first we write f of x. I stated yesterday, but maybe it's better if I restate it today. So I just stated in a form which is somewhat, let's say, inaccurate, but we understand it. So inaccurate only in the sense that I would need to make several assumptions that I'm not quite claiming. So this is less or equal than f integral f. So f convex, let's say on R. Then of course we should, sorry, I wrote something that is entirely stupid here, of course. So this is f of the integral. Okay. So of course we should at least assume that this integral exists, not necessarily finite, and this integral also exists. Okay, so this inequality, of course, it is interesting when the integral on the right hand side exists. So if the integral on the right hand side exists, it says that also the integral on the left hand side exists, provided this f is integrable in the sense of Riemann, if this is the best integral you've looked at, and then the inequality is correct. Okay, this is not the most general version of the inequality that would require, let's say, instruments that we do not have for the time being. So this is the same that I claimed yesterday. I gave a very quick proof. Today I write it a little bit better. So the function f of x can be written as the supremum of aix plus bi. Now, the fact that we can choose, in fact, these i's in a countable set, so in n, at this point does not play a role. So I just write it like this. So this means that if we apply it pointwise, so if apply pointwise this identity, so we have that f of f. So this is true for all x real. So we look at this applied pointwise. So this is larger or equal than aif plus bi. Okay, for the function that we are looking at. So now the only thing that we need to do is to integrate on both sides. So you see that we integrate here and with respect to mu, and we integrate here with respect to mu, and you see that we also have to integrate 1. So we need a very important extra assumption here that we will somewhat relax later, And the hypothesis that we need, other than convexity, is that the integral of the function 1 is 1. Okay, which is equivalent. Remember that our convention, this is equivalent to the fact that the function mu x has integral 1. Okay, so this is in order to having here integral of 1 equal 1 and to leave it like that. Now you see that if we take the supremum on both sides with respect to I, so these are just numbers, so we are left with integral of f d mu larger or equal than f integral, which is what we wanted to prove. Okay, and notice that this assumption was very important in the proof. We can somewhat relax it, but we cannot use it for weights mu that have infinite integral. So how do we relax that inequality? Well, it is rather simple. In fact, we define another weight. We define a weight mu tilde, and this weight mu tilde will simply be defined by 1 over the weight of either the whole, let's say the whole R, to keep it simple, and then here mu x. So remember that, or maybe I think I already said that, but I'm not sure. So remember that whenever we write mu of a, this means just the integral of the function, indicator function of a, d mu. Okay, this is what it means. So if we do this, then we can apply, we can just write the usual. So clearly now the integral of 1 d mu bar, this is in fact equal to 1. So there is no problem with that, right? So this implies that we can apply the Riesz inequality that we have just proved. So we can write that f of the integral f d mu bar is less or equal than the integral of f of f d mu tilde. Okay, but what does this mean? This means nothing else than f integral f, and then this, remember that we have this definition, so there is a 1 over mu r here, and here there is the usual d mu. This is less or equal than the integral f of f d mu 1 over mu r. Okay, so we have this replacement, and note that we absolutely need that this is finite. Okay, so for this to make sense, we need that this is finite. So in other words, we have another version of the Riesz inequality, not necessarily when the measure of the whole real line is 1, but just when the weight, for us this mu plays the role of a weight, when we have a weight function whose integral over the whole R is finite. So let me briefly mention why I told you something about that fact that we can restrict the supremum to a countable number of points. The reason is the following. It is similar to something that we already looked at when I said that you can write the Hölder's inequality also taking more general algebraic operations, or let's say certain family of operations that respect some algebraic properties. Properly said, I should say this. So let us start again from the observation that we take the function f of f, and the start of our proof is just that here we have aif plus bi. And as we said yesterday, we would like to apply a certain operation. For the time being, we don't say from where to where. So, and here we have something like this. So if we would like to mimic the proof that we have done so far, you see that, so here, if we have linearity of t, if we have linearity at this point, there is no real issue. So we write AITF. plus bi, but here we need t1, right? We need t applied to the constant function 1. So what is this? So if we make the assumption that t1 is equal to 1, or you see that in fact all we need is that t1 is larger or equal than 1, as a matter of fact. This would already be okay. So we would have that this is aitf plus bi. Now, it is exactly at this point where t is a general operation, let's say, that it becomes important to be able to say that I belongs to n. So that we can take the supremum over a countable set. Why is that? I cannot explain in detail the whole thing, but the principle is the following, that if you assume that the codomain of T, so the space or the set where T maps the values of F, satisfies certain minimal condition, this minimal condition that it is often used in mathematics, in analysis, behaves very well only with respect to countable operations and does not work well with respect to uncountable operations. So this very minimal, let's say, smoothness assumption or regularity assumption, smoothness is too much because it has already another meaning in analysis. This minimal regularity assumption that one wants to have when we look at more general operations T than just integration or summation. For instance, I repeat, when functions f are mapped to other functions, is called measurability. We do not discuss it now. And measurability is preserved, so roughly speaking, measurability is preserved under countable operations, while it is lost under uncountable operations. So the simple observation that we do in fact have that we can take the supremum of this right-hand side with respect to a countable number of indices allows us to say that for a rather large class of these operations, we have that T f of f is larger or equal than f t of f. And this could be interpreted, again, pointwise for a certain codomain of the operation T. So instead of mapping, so integrals map functions to real numbers. Here we're saying that we can allow more general operations that take functions to other functions, as long as they are linear, for instance, not strictly necessary actually to be linear, because as we said yesterday, you see, if you want to have this, we would have just positive homogeneity, and in this case, not sub-additivity, but super-additivity. And by the way, this is a problem because most interesting operations T that are used in analysis are not super-additive, but sub-additive. So you see that one would think that then, well, then maybe there is no such thing as a Jensen's inequality for this type of operators. Well, these operations, let us just call them. In fact, one would have much better luck if instead of using convex function, uses concave functions. In that case, you would see that you have a good way of mixing things, and one can allow even this extra generality. Anyway, let us repeat, if we have linear operations T that are such that they map the function 1 to the function 1, then under very minimal let's say regularity assumption that goes under the name of measurability that you will see probably in the before the end of your career, undergraduate career, then there is an analogous version of the Jensen's inequality. Okay, so this is something that is quite interesting. Now, I would like to give another little application of the let's say, we could call it of the Jensen's inequality, but in fact it is just a very simple direct consequence of convexity to give an alternative proof of the Minkowski's inequality. So with the proof of the Jensen's inequality for integrals, or for this general set of operations, I put on, let's say, sounder ground what I showed yesterday in a rather too quick way. So let us repeat that the Minkowski's inequality is the following: that if we take two functions and we look at this norm P, now we can call it a norm because we have already proved, in fact, the Minkowski's inequality in just as an application of the Hölder's inequality. So this is less or equal than Fp plus Gp. Okay, I would like to show that we can indeed get the proof also by using convexity ideas. So, sorry, I refocused this because it looks a little bit blurry. Hopefully it's slightly better now. And the idea is the following. So first of all, assume, as always, that f plus g is equal to 1. We can do this by homogeneity. By the way, remember that this was our main example of an inequality that is homogeneous in the couple fg, in the pair fg, but it is not separately homogeneous. Okay, so it means that if you multiply f by lambda, you do not get on any one of the two sides, you do not get positive homogeneity. Okay, so let's see how we would prove this. This is slightly more interesting, more interesting, let's say, than the analogous proof that we gave for the Hölder's inequality. It was extremely quick. You remember, in that case we said this can be set equal to 1, this can be set equal to 1, and then everything became just a very quick application of the AMGM inequality. Here we need to work a little bit more. And first of all, we need to insert some convexity somewhere. So, sorry, by the way, I did something wrong here, because the correct one is this. So this assumption actually suggests what to do. So we fix lambda equal to f plus g. And of course, you immediately see from this that 1 minus lambda then is nothing else than g over f plus g. And now we should be able to take into account the convexity of the function. So the function x to the power p is convex, and we should exploit this somehow when we take it pointwise on the couple f plus g to the power p. So let's see what an idea would be. An idea would be to try to pass from this expression to something involving lambda and 1 minus lambda. A combination of something. Of course, if we do f and g here, this is not really meaningful. It makes it does make our life easier, but an idea is the following one. Is to do this, to take f, then we normalize by f, and then we write plus g, and we normalize by g. If you put the definition of lambda and 1 minus lambda inside here, you will see that we get simplification, and we end up exactly with f plus g there. At this point, what do we get? We get, remember, we are also using the fact that f plus g is less or equal to 1. This will lead us to lambda f to the power p over f to the power p plus 1 minus lambda g to the power p g to the power p. Now we integrate both sides. So we integrate f plus g to the power p. This, of course, will produce f plus g p to the power p. And this will be less or equal than lambda 1 over f p p. There is a p here. And then integral of f of p plus 1 minus lambda 1 over gpp integral gp, right? But then this by definition simplifies with this, and this simplifies with this. We are left with lambda plus 1 minus lambda, which is 1. And this is in fact by the normalization assumption, this is the sum of f plus g, and we need an exponent p because we have an exponent p here. And this completes the proof, which was just a quick application of convexity with this little bit of playing around here with a normalization idea, which we have used already quite a few times. So I don't think it is very surprising by now. Okay, so let us consider now some further consequences. I don't think I have time to do all I wanted to. So maybe I will take this approach. So instead of proving more things, I will just tell you some interesting consequences of the Hölder's inequality, and I will just write all the proofs in the notes. But for here, I just briefly mention what we can obtain. So there is a very interesting corollary to the so-called quasi-linearization that we proved yesterday. So that was the following fact, that if we have a function f and we are after its norm p, this can be obtained by looking at the supremum of the integral of fg over all g such that p prime is less or equal than 1. The p prime norm is less or equal than 1. So we proved this entirely, and we actually proved it that by saying that one inequality is very easy and the other one is proved but just by examining the case of equality in the inequality, which came from the equality case of the AMGM inequality. Then this observation has the following corollary that, as I said, I'm not going to prove, but it is very interesting because it says something apparently complicated, but in fact quite simple, which is the following fact, that if we have 0 p q, so in this, they are just used as exponent for us. And now I state something, so for every, I state something that I have to explain. So first I write it, then I explain it, and it is this, that f LP LQ is larger or equal than f LQ LP. What does this mean? So it means the following, that I define f of LQ LP, I define it in the following form. So first, so I take a function of two variables, x and y. So first I take the pth norm. So I take p here. So let us take f positive, because we know that in any case we reduce everything to the absolute values, so there is no point of writing a bunch of absolute values. And I integrate with respect to let's say to the variable y, where we have the weight nu. So as I said, first I take the pth norm, okay? Then this will be a function of x, and I can take the qth norm. How do I do this? Well, I take q here, integrate with respect to mu, and the whole thing I take the power 1 over q, okay? So this is what I defined as QP norm. So it says first I take the P norm in the variable x, then I take the qth norm in the variable, in the variable y, then I take the qth norm in the variable x. So this says that if you have p less than q and you swap the exponents, then the sign of the inequality, so p less than q, becomes larger or equal. Okay, less or equal turns into larger or equal. So less or equal and flipping turns into larger or equal. So this is a mnemonic way of remembering it. This proof simply applies the fact that when you want to write the norm, the pth norm, you can write it as integral of something with respect to a certain g of p prime norm less or equal than 1. Okay, and then the idea of the proof is to exchange the order of integration and to prove that in the exchanged order of integration you end up with this new arrangement of exponents. In other words, this as a particular case, let's say, of this inequality, we have the following rather useful inequality that you can apply plenty of time, which is the following: that if you have a function f, let's say, let us write it like this: if you have a function f x y nu dy, and then you want to look at this function as a function of x, and you apply to it the norm r, let's say, okay. So in the sense that so let us write like this then: you look to this function as a function of x, then this is less or equal than the integral of f of which you take the r norm and then you integrate nu dy. Okay, so this hardly complicated inequalities can actually be proved to be equivalent to this inequality. Okay, this inequality, as a matter of fact, and this inequality are the same only from a strictly, let's say, computational point of view, because in order to say things completely, we will need a lot of extra knowledge that we are not going to discuss at all. Okay, but in any case, at least to do computations, this can be applied very profitably. And also let me mention that everything I wrote is perfectly precise, but there are some technical assumptions that need to be added in order for the objects that I've written to make sense. So in other words, supposing that all these objects are well defined, these inequalities are true. Okay, so the point is within within the Riemann integral, we cannot give the necessary, we cannot give the sufficient regularity conditions on the involved function f in order for all this to be meaningful. Okay, so this is something that I apologize for. I don't think I have any extra time. Should I stop here, or do I have another 5 minutes? Can I take another 5 minutes? Just tell me.
Yes, I think you have 5 minutes. Yeah.
Okay. So.
Okay.
There is another quite important property of consequence of the Hölder's inequality that I wanted to discuss, which is a very natural question. First of all, I ask you to check something by yourself. So I propose an exercise that is the following. Suppose that we have a function mu, so a weight which is finite. Then take as before 0 pq. And now the question that I would like to ask is the following: if f q is finite, can you say something about f but p? And then same question, if mu r is equal to infinity, can you say something? Same questions. So same questions if mu r is infinity. So you will see that the two cases are completely different. So in case one, you can say something. In case two, you cannot say anything. You may have this finite, this infinite, or this finite and this infinite. Okay, so they are not comparable. But then there is a rather then another question arises, which is the following one. So suppose we have now 0 p and q, but not equal, strict inequality, and we take r between p and q. Let's say we take r between p and q. Now the nature of the question is the following. Suppose if f p is finite and f q is finite, can we say something about f of r? And the answer is yes. And there are two famous inequalities that answer this question. One inequality is due to Littlewood, who was an English mathematician. And another one is due to Lyapunov, who was a Russian mathematician. And I just show you one of the two, and the other one I leave it to you to go look for it. Okay, so I just give you maybe which one should I give you? I'll give you the Lyapunov inequality. So Lyapunov. So suppose that r being in p and q, of course we can always write that r is equal lambda p plus 1 minus lambda q. Then we have the following fact. We have that f r to the power r can be dominated by f of p lambda r and then f q 1 minus lambda q. Okay, there is a similar inequality by Littlewood, and maybe you could look for it. But this inequality is very useful, and as an exercise, which is actually a trivial one, but fun, show that the function that takes p into the log of fp is convex. Okay, there was I have one or maybe I take there was one thing that I announced in the abstract of this course that I hoped to reach, and it is in some sense a generalization of this type of ideas. So this type of ideas trying to bound something between with an exponent between a range of exponents, giving information about the extremes of the range of exponents is a very widely studied topic, which goes under the name of interpolation. So there is a very powerful result with a rather unexpected proof, which is an inequality for these things that I called operations. I should call them operators, not operations, but since we don't have the terminology, I chose this alternative way, which says, roughly speaking, the following. Suppose that we have P0, Q0, and we have P1, Q1. Okay, I give just a pictorial idea of what is going on. And suppose that we have, let's say, we have an operation T that take function with P0 finite norm into function with Q0 finite norm, and T does the same for this other couple of indices. Then it says that take anything inside here, take any other index inside here, take any other index, and the operator, this operation will behave in the same way. So you take any R which is between the two. Okay, well, I cannot call them R's. Let's say R0, RS. Let's say RS. Okay, and in the following way, that 1 over R is equal lambda 1 P0 plus 1 minus lambda 1 over P1, and 1 over S equal lambda 1 Q0 plus 1 minus lambda 1 over Q1. So you see that the way you choose R and the way you choose S cannot be, of course, completely independent, but they need to satisfy this convexity condition. So convexity on their inverse. Then it turns out that the operation T again behaves in the expected way. So it maps function with R integrability to function with S integrability. So this the proof of this result is due to mainly to the second guy, to Thorin, who was a Swedish mathematician. And there is a very nice, interesting proof with a slight, with slight less generality than the Riesz and Thorin theorem, which says that if you take T to be a positive operator, all you need in order to prove this astonishing theorem, very strong theorem, is just the Hölder's inequality that we have proved in our course. Okay. So this is the statement of the theorem. So if T is positive, which is the property that I call positivity preserving, then proof requires only Hölder. Let's say I write in quotation marks for T. Okay, so for the alternative version, that instead of taking just integration or summation, you take an operation T that has some decent properties, positive homogeneity and linearity, and T1 equal to 1. Maybe in this case we don't even need that, as a matter of fact. Okay, so out of curiosity, I will just if I have time, I will write I will write the whole proof in the notes, maybe not in the very first version that I will give you today or tomorrow, but maybe in a few days, by mid next week, something like that. Okay, I don't have time to prove it. I wanted to show to you how to do it, but okay, I hope that at least I somehow I arouse your interest for this type of results, and I should stop here because I'm already 5 minutes late. Thank you very much.
Okay, many thanks, Carlo, for your very interesting lecture and for excellent mini course. So now I'll stop recording, and